to raise the question of whether flaw are important or not, it turns out that's just a question of whether the nominal strength is comparable to the perceived strength that you evaluate in absence of flaws. So I want to turn the page. I want to indicate that I motivated this point sufficiently. We even start to talk about how stress could stop building at the tip. But let's come back to that later. And now let me review the part I think you heard about before, right? Which is the elastomeric case. So I'm anxious to show you more troubles in the case of in the case where polymer is elastomeric rather than plastic. And later we would describe both in a clear story here. So I'm repeating what you heard many times already, that, okay, so this is notch free, so don't notch. When you have no notch, supposedly you are dealing with a piece of science that's not fraction mechanics, unless there is flaw that you perceive in the system. So I actually once mentioned that today, most people probably, for a fairly stretchable elastomer, could agree that there are no flaws, which means they are similar. Under that circumstances, this occurs. And this is a data that's by Thor Smith, 1958. And what's plotted was this nominal strength as a function of the rate of stretching at different temperatures. So exactly what I have indicated to you before, that at any given temperature, you can stretch more as you use higher rate to stretch it. Each point is the point denoting so-called tensile. That's a very simple term. It's called tensile strength. Basically, the engineering stress at the point of fracture, rupture. So this is a result nearly 70 years old. It is absolutely the essence of elastomeric failure. It is, in other words, this is the only thing there is you need to deal with. So let me first indicate my claim that this nominal strength, I know this particular figure used sigma f, which in our notation is just sigma b. The nominal strength. The nominal strength has the same name as what I just said, tensile strength. Okay. Look at this. This is a double log. This is the way I showed you guys never plot double log this way because they take a 10 and then reported the exponent of 10. So I cannot read where is 2, where is 3, where is... but I can read this as 10. I can read this as 100. Okay? So you can see the strength increases, and this is what? 10 to the 0, that's 1. 10, 100. And so you can see that depending on temperature, the strength of your polymer increases about 2 order magnitude, but never really larger than 10 megapascals. And in the homework that you supposedly just did, I asked you guys to, because I omitted in the lecture, I asked you guys to estimate the theoretical strength. I just wrote down the solution and submitted to Brightspace about it. And you will recall the ideal strength would be something like 4 gigapascals, much, much greater than this. I think, without putting words in everyone's mouth, I think it is not terribly controversial for us to suggest that you only get 10 megapascals because any given time only meaning 1% of strength is loaded, or even less. So we get away from the question of whether flaws are the one reduces it. So let's ignore that part. Well, historically, you should never ignore that part, because historically, this so-called notch-free problem was exactly understood as happening involving flaws, so that the understanding of this flawless, I misspoke, the understanding of this notchless sample is understood through the framework of fraction mechanics. So by now, I hope I confused you enough, because I said both things. Ignore it. Just let me give you the rest of the. Ignore it because for 70 years, for 99% of all papers shy away from this notch-free problem. Why bother if this is all just a flaw infected problem? Let me make a cut and study the resistance to cut, which brings you back to fraction mechanics. Okay. I came from an angle where eventually I'm going to settle down to show you that this is not a flaw problem. In other words, I will eventually show you that we can experimentally determine that this is true in the red box. Yeah. Yeah, I'm just trying to save some time now. Yeah, exactly. No, don't mix that. That fiber limit was a way I was trying to explain how you visualize plastic state, the fact the chains are coil, not fibers. In the homework on ideal strength of elastomers, we were considering the coil state, actually. And in that even coil state, you get several gigapascals, because we assume all the strands bear load. So it's different involvement of how we estimate the theoretical strength. No. In the plastic case, it's also a coil. But the literature tend to use this chopstick limit to indicate that there is several order magnitude difference. So it reflects some confusion about why you even bother to mention chopstick limit, because it's not the limit. Your sample is coiled. But I invoke the chopstick limit because I'm allowed to write the inherent, our perception of strength in terms of chopstick limit times 2/10. If you it's right here. So right here. So this is just take a ride, free ride. I'm just trying to neatly express everything in that form. But I probably there's no need for me to impress you for the rubber case. In the rubber case, even isotropically, I can show you it's much greater by assuming all the strands bear load, which is wrong, apparently, to assume so. Yeah. So indeed, I kind of counting on you to realize that this part of the discussion is somehow, in some sense, related to plastics, whereas now I want to come back to the elastomeric case. Okay. You can imagine if you don't think there are flaws in this, I call it notch-free or notchless sample, if there are no flaws, how on earth you want to explain this? Because you cannot bring in fracture mechanics. Okay, you cannot bring in fracture mechanics because it's a homogeneous system. As I said, 1955 is when WF discovered time-temperature superposition equivalence. So people start to superimpose. And as I teach you in doing a superposition, you can measure your G prime, G double prime by different temperatures. You find out the way to construct a master curve is to horizontally shift. And that's because your function are indeed only a product. The variable in your function is a product only of the frequency and relaxation time. So the point here is upon seeing this, or certainly a few years after this, people start to do the same thing, make a horizontal shift. Why not? So the sitting at this temperature is equivalent to sitting at a colder temperature and apply less stress. So I plotted it almost. I draw this point in the sense they are on the same horizontal position. That sounds about right. Decreasing the temperature is the same as increasing my omega in your learning of how time-temperature superposition works. So we do that. So you can see this will be, by doing that, this triangle will be shifted to here. And this square will be shifted to here. And so on and so forth. And this triangle will be shifted there, so you get some kind of master curve-like thing. So this shift essentially involving saying that the rate you use, and shift, if you still recall, is about WF shift, and where A is nothing but relaxation time at one temperature relative to a reference temperature, such as glass transition temperature. In other words, what I'm saying is that when you do such a shift, it basically involving recognizing that your quantity is determined by the rate and the relaxation time, or better yet, is determined by the rate and viscosity. Because we know in our polymer physics, they are changing with temperature the same way. The modulus changes with temperature negligibly, so we don't, right? We don't need to bother with that. So at the end of the day, you are claiming that your inherent strength is a function of this quantity. What is that quantity? Well, isn't that just Newton's viscosity? Meaning, sorry, Newton's viscous stress. So this has a terrible, terrible implication that I only recognized it 5 weeks ago, maybe. Meaning I was already smashing this like no tomorrow, but it just takes so long to get to all the juice out. And you realized it speaks about this strength has the origin that's entirely viscous. Right? Because it's a viscous stress. I can, so how I also want to say, in fact, perhaps we are among the few who you have the benefit as well. We are among the few who knows enough about rheology to know that the origin of the stress is nearly entirely elastic, which means interchain in origin. Rather than interchain friction. In fact, the way we prove that's the case is using so-called in situ birefringence. So I'm only verbalizing it because I think otherwise I may run out of time. So basically, you could show, for example, when you have, so just use engineering stress. When you have stress as function of, just call it lambda, which is the ratio, you will basically see that I think this is where it's so crazy, it's not even funny. So first thing I can give you a complaint. This paper is done this way without showing any SS curves, meaning I call the raw data. So I could only speculate based on other data that when you change rate, you don't even find you don't even find the curve to deviate from each other, except at this rate it breaks here, at higher rate it breaks here, at higher rate yet it breaks there. That's almost like a quiz generally for you as a rheologist. This feature would mean the whole system is purely elastically stretching. I think I recall telling you guys a different scenario. I kind of recall doing it, that you could have a case where the low rate does this, the higher rate does this, and higher yet rate does that, or which means at any given amount of stretch, the stress is different. That's all I'm saying. I confirmed a couple of weeks ago, there are enough confusion to think that this higher stress is because there is a viscous component to the elastic component. I think my discussion of polymer rheology was so sketchy, I didn't even indicate much about why you develop a rate dependence of the stress response. So it turns out you can do so-called birefringence, which is a measure of how much chains are stretched and how many are stretched. You'll find that as you go to higher rate and finding higher stress, your birefringence proportionally grows. So you can make a measurement and essentially not only proportion the growth, unless you drive the system to go crazy to very high stretching ratios, they are even linearly related on this double linear plot. So this allows you to rule out. So I'm indicating, for example, your red will be here, your green will be here, your black will be lower. In other words, this lower stress is accompanied by lower birefringence and vice versa. So that the nature of this stress increase is entirely intra-chain, meaning. And in fact, it comes from trapped entanglement. So remember, this is a cross-linked system. In fact, I should, just for your information, something of this sort also occurs for even non-cross-linked systems. But in general, this is a feature of how much entanglement comes in, which is, of course, measured by how fast you are stretching. Yes, Charles. Where? Which second first? Third. God. Yes, I just, it's delta N, so it's birefringence. Delta N, not eta. Yeah, so I shared so much information here, but so let me slow down. So this is all we have to say. Your dear polymer is really elastically stretched, and the business of this shifting, suggesting this thing is, you must admit this thing is entirely viscous, is outrageous and has no place. Do you follow that logic? So that if you think you have successfully used WF to shift, it would have implied that you insist the nature of this, why it changes with this product, or what is this product? This product is viscous stress. So of course, you stretch slowly, it breaks here. If you stretch much faster, it breaks much later. It implies there is internal clog. Be my guest if you want. I hate to say this is a viscoelastic thing that treats this internal clog as Maxwell. I probably should avoid doing that, except to say somehow, you see, it's so trivial, it's not funny. Let's say I stretch to a lambda, let's say I triple my length, it breaks at one rate, okay? Okay, so I triple the length, it breaks. Lambda equals 3. Now I'm going to use a rate 1,000 times faster, okay? Let's say suppose it breaks at 7 now, instead of 3. Do you know how little time is spent to reach 7? 500 times almost, right? Because didn't I just say 1,000? And 7 divided by 3 is another factor of 2. In other words, when I use a rate 1,000 times faster, by the time I reach just 3, I have spent negligible amount of time compared to the first rate I used. Yes, fair? And somehow there is a clock in my elastomer that is quite aware of this. So I'm insisting that this rate effect must reveal that there is something doing some timekeeping there in my system. Same stretching amount, therefore same stress level, same bound tension. Of course, you know the answer. Same bound tension. Instead of spending 10 seconds here already, it spent what? 10 milliseconds, right? 1,000 times faster. And 10 milliseconds is not a lifetime for that network to break, because network breaks at 10 seconds. What do you do? You march on, meaning you stretch more. As you stretch more, the lifetime starts to shorten because you are building more tension in the bond. And there will be a point that the lifetime is as short as about the time you are using to stretch. And it necessarily involves a shorter time scale, and the shorter time scale necessarily involves a higher stress because if I use this general expression, because on shorter time scales, when t is short, it means E. When t is short, it means E is also short, small. E is small, correspond to tension high. So I know this, you need to switch your mind that the high tension is what brings down the activation barrier. And high tension, of course, means higher level of stretching and higher levels of tensile strength. So you have to get used to this idea that your material is simply stronger on shorter time scales. It's why very simple one word to summarize everything. So I have already said, no puzzle. You have your clock. That clock is provided by the bond dissociation kinetics. So on one side, I told you it's not polymer relaxation time. On the other side, I showed you what it might be. Because it cannot be polymer relaxation time, because I told you it's not a viscous process. I guess I may be still quite rushed when I talk about all this, but there seems to be no other way out. Of course, I can tell you, until this moment, this idea of suggesting the internal clock is provided by the bond dissociation. You can see this expression, of course, it looks familiar. It looks just like the iron activation expression. And so it's just another form of activation, except this activation is to break the chains so that you can stop suffering from the stretching, which is to terminate the stretching. So if anything I can offer is to say, until recently, the paper, within the year or so, prior to that, we thought this whole problem is still just, so people use the word, the nature of this thing is viscoelasticity. I post something and say, please don't use this word until you know what it means. So what it means, of course, we first learned it from a Maxwell model. It says the nature of a viscoelastic material is such its mechanical response really depends on what time scale you're looking at it. When you have a purely elastic material, it does not matter what time scale you're looking at it. The response is the same. And that's the limit of no viscoelasticity. Yet, it breaks at different levels when you use different rate. How perplexing that is. In other words, you can go to this non-viscoelastic limit. This is a non-viscoelastic limit. Okay? There's no viscoelasticity. And I perceive this condition quite well because you need to do nothing in a hurry because your chains are all fixed. Its response doesn't care how fast you're stretching it. There is that limit accessible to you. And in that limit, this still occurs, meaning the material is still stronger when you stretch faster. How frustrating. I mean, so that's how we did it. We did it in two steps. Find the case where it's purely elastic. In fact, this case is still just now being worked. You know, we're writing a paper just on this, where you're confused about what is viscoelasticity. Let's see what is viscoelasticity, or where viscoelasticity come from. Speak of anything, you have to have origin. Remember I repeated a million times. It's written in. I think it's written in the preface of my first book. Whenever you have viscoelasticity, you should be reminded there must be a structure that produces the elasticity in that word of viscoelasticity. And that structure is transient, as a lifetime. And in fact, you can go on to the nonlinear response. You can force that structure to break down on time scales much faster than the willing time scales that they want to relax. Or we call it voluntary yielding, if you still recall that word I said. So viscoelasticity, anytime anyone invokes it, go find what is that structure before you speak. And what is that structure? Additional. In the case of elastomeric, because you already have the structure of the network due to cross-linking. This is additional and shows up progressively stronger if you're willing to use higher rate. And we are quite familiar with it from rheology. There's a transient structure that can be more elastically probed if you probe it on shorter time scale. And be more explicit, it's conceivable that structure is this uncrossability producing entanglement. And the way you can call it embedded or trapped entanglement. Basically, especially the way you make your polymer is to start with the entangled melt and then cross-link a few places. Necessarily, you trap the entanglement, meaning track the topological constraints between chains through uncrossability. So depending on how fast you're doing it, this red and black chains may or may be engaged in producing this extra quote-unquote cross-linking point here, right? So that depends. Any questions? We can bake some questions by having a short break. Indeed, I mean, I don't want to lose you. This is we're reaching a point where there's no point to